Now, let us start with numerical on Raimondi-Boyd method, one of the methods used for lubrication analysis of hydrodynamic bearings. This numerical was asked in one of the universities in June 2011. So let us proceed with the numerical. 75 mm diameter, journal diameter is given. Full journal bearing runs at 400 RPM, revolutions per minute, capital N, revolutions per minute is given. It is 75 mm long, bearing length L is given, subjected to radial load W of 2500 Newton. Whenever the load is given in kilonewton, you will have to convert it into Newton when you are solving it by Raimondi-Boyd method. Here already it is given in newtons, 2500 Newton. The bearing is lubricated with SAE oil 30 with a viscosity mu of 16.5 into 10 raised to minus 3 kilogram per meter second. Raimondi-Boyd method, the absolute viscosity should be in Newton second per mm square. So we'll have to do the conversion. Flows into the bearing at a temperature of 75 degrees. See, the radial clearance small c is 0.03. What is asked in this numerical? They are telling to find out Sommerfeld number. It's not Sommerfeld, it is Sommerfeld. There was a printing mistake in the university exam question paper. It is not Sommerfeld, it is Sommerfeld number. So the first thing that they have asked is Sommerfeld number, capital S. Minimum oil film thickness, HO. Attitude, actually it is eccentricity ratio. They're telling us to find out eccentricity ratio. Power lost in friction, heat loss, side flow, QS in terms of the Raimondi-Boyd method, total flow, Q, temperature rise. Let's start with the numerical. Yeah. So let's first mention the given data. Like I said, the first thing given is the journal diameter, revolutions per minute, that is capital N. It's in revolutions per minute. We will have to do it in revolutions per second. Bearing length. So obviously our L by D ratio is 75 by 75, that is 1. Radial load, W. Radial load, W, which is 2500 Newton. Viscosity, mu. Absolute viscosity, which is in kilogram per meter second. Like I said, we'll have to do the conversion. Radial clearance in Raimondi-Boyd method in Bhandari design data book. It is radial clearance. If you go by PSG design data book, it is diametral clearance. I have solved this by Bhandari design data book, but how to solve it? If there is a PSG design data book which is allowed in your exam, then numericals with PSG design data book are also available in my YouTube channel. You can go through that. Now, moving ahead. So guys, first thing first is that you have to find out L by D ratio. Length of the bearing is 75. Diameter of the journal or shaft is 75 mm. So L by D ratio, dimensionless parameter. The first dimensionless parameter always in Raimondi Boyd method is the L by D ratio. Without this, you cannot proceed in Raimondi Boyd method, because if you want to go through the table, you'll have to first find out the L by D ratio. I'll show you how. But before that, let's do the conversion of viscosity. How much kilogram per meter second is how much Newton second per mm square? Because like I said, in Raimondi Boyd method, you have to do the conversion in Newton second per mm square. 1 kilogram per meter second is 1 into 10 raised to minus 6 Newton second per mm square. Then 16.5 into 10 raised to minus 3 is how much? Then it is 16.5 into 10 raised to minus 9 Newton second per mm square. You'll have to do the conversion of units of absolute viscosity from kilogram per meter second to Newton second per mm square. Otherwise, you will not get the correct answer of all those things which are asked to you in this numerical, whether it be Sommerfeld number, minimum oil film thickness, attitude, everything will go wrong if you're not converting it from kilogram per meter second to Newton second per mm square if you're using Raimondi Boyd method using Bhandari design data book. Moving ahead. Now, like I said, first things first, you'll have to find out what is the L by D ratio. Obviously, before this, L by D ratio for infinity is there. Then L by D ratio for 0.5 is there. 1/4 is there. But mostly L by D ratio numericals for L by D ratio 1 are asked in most of the university exams. So I've put this table over here, which you'll find it in Bhandari design data book as well. Now, the first thing arises is that where should I start from? The method is first find out L by D ratio. And for that, one of the parameters, either attitude or eccentricity ratio, HO by C, Sommerfeld number, angle, R by C into F, coefficient of friction variable Q upon RC NSL, QS by Q, anything, any one of them should be known to you. Or you'll have to first find out any one of the parameter based on L by D ratio. Then in our numerical, you are being told to find out this attitude. So this is not known first. You are being told to find out HO. So this also is not known. You are being told to find out coefficient of friction. You are being told to find out total flow. You are being told to find out side flow. So the first thing that you can find out in this is the Sommerfeld number based on the given data. You do have R, journal radius, radial clearance, absolute viscosity, revolutions per second speed of the journal. Pressure is not known, but whatever is required to find out pressure, that is there with you in the numerical. Load is given, radial load, length is given, diameter is given. So what we'll do, we'll first find out the bearing pressure. On basis of that, we'll find out Sommerfeld number. So for L by D ratio 1, you will probably get one of the Sommerfeld numbers. On basis of that, in front of that, those values will mention and you'll find out the other values. But it's not that easy. Let's see what's happening. So, like you see here, load is given, length is given, diameter of journal is given. So we found out pressure. On basis of this pressure, we can find out Sommerfeld number, whose calculation I've done here. If diameter is 75, radius will be 37.5. Clearance is given. Conversion of absolute viscosity in Newton second per mm square, we have already done before, 16.5 into 10 raised to minus 9. Ns is nothing but n by 60. N is 400 RPM. So n by 60 is Ns. Pressure, you already found out here. So by putting all these values in the formulae of Sommerfeld number, you'll get the value of Sommerfeld number as 0.390625. Let's assume Sommerfeld number is 0.39. And let's proceed towards the table for full journal bearing. Now, if I try to find out 0.3, directly that value 0.39 is not available. So I'll have to do the interpolation method. I'll have to use the interpolation method in the finding the performance variables for hydrodynamic bearing, full hydrodynamic bearing. 0.39 obviously lies between 0.2 and 0.6. It won't lie between 0.2 and 0.1. Obviously, it will lie between 0.2 and 0.631. 0.264 and 0.264. Now, the first thing that is being asked is minimum oil film. First was asked Sommerfeld number, which we already found out. It's 0.39. Then the next thing asked is minimum oil film thickness, which we have to find out from this ratio of minimum oil film thickness divided by radial clearance, which is available here. So now we are going to see if Sommerfeld number is 0.631. In front of that, this HO by C value is 0.8. Same way, if Sommerfeld number is this 0.264, then in front of that, this HO by C value is 0.6. So if 0.39, which somewhere lies between these two values, then what is the value of HO by C for this 0.39 Sommerfeld number value? So I'll use a simple interpolation formula. I'll name this as X1. If I name this as X1, then corresponding to that X1 value, this is your Y1 value, right? Same way, if I see X2, then for X2 value, 0.631, I'll get a Y2 value, which is 0.8. So I've named it Y1, Y2. You can reverse those, but still you'll get the answer. How? Let us see the formula. How to use the formula. Interpolation formula. It's Y1 minus YR is X1 minus XR equals to Y1 minus Y2 is X1 minus X2. I can if I can name this X1, this will become Y1. If I name this X2, this will become Y2. I can do either of the ways. That's not an issue. We'll still get the same answer. Like I've done reverse of what is written here, so that you can understand that anyways that is correct. But you should note down that in front of 0.631 Sommerfeld number, the HO by C value is 0.8. And in front of 0.264, HO by C value is 0.6. When I put these values, into this equation, like, let me show you. Y1 is 0.6 minus Y2 is 0.8 divided by X1 is 0.264. X2 is 0.631. Same way, Y1 is 0.6. YR is unknown. That's what I want to find out. X1 is 0.264. And XR, Sommerfeld number, in front of which I want to find out HO by C, that is 0.13, and that is known to me. So now let's move ahead. Simple calculations need to be done here. When I'll do this part in my calculator, I'll get this as 0.545. When I do this part in calculator, obviously answer will be in minus. This will go over here and multiply like this. I'll get the answer as negative value. Now negative YR will go this side, will become positive YR, and negative value will come and this side will become positive. The answer comes out to be 0.6686. Let me assume at 0.67. Obviously, you can see here if 0.39 is somewhere here, Sommerfeld number, then in front of that HO by C value, I'm getting 0.67, which is very correct. Logically, it's true. So this is the answer for HO by C. I've still not received HO. My target was not finding HO by C. My target was to find out HO. So HO by C, I found out this value to be 0.67 here. C is known, which is 0.3. It will go and multiply here. HO is 0.02. This is my second answer that I found. Very quickly, let's go to finding out the attitude or eccentricity ratio. Now, in front of 0.631, eccentricity ratio is 0.2. In front of 0.264, it's 0.4. But what about 0.39, which lies between these two values? I'll have to find out by interpolation. So let's start. Same way, I'm just giving these values. So if this is X2, obviously this will become Y2. If this is X1, obviously this will become Y1. And if this is XR, what is this value in between? That's what I want to find it out. Obviously, we are going to use the same formula for interpolation. Y1, 0.4. YR is unknown. X1, 0.264. XR, 0.39. Same way, Y1, Y2, X1, X2, just by doing the simplifications, which I've done it for you, I'm getting eccentricity ratio as 0.331 for 0.39 Sommerfeld number. This is the value. What is the next thing that is asked? Let's find out. The coefficient of friction F. Where can I get coefficient of friction F from this formula? R by C into F, radius of the journal, radial clearance, coefficient of friction. Again, like I said, 0.39 Sommerfeld number lies between these two numbers. Then in front of this number, what is your R by C into F variable? Magnitude of that variable I need to find out first. Then I need to find out R by C into F is equal to that magnitude. And then I need to find out coefficient of friction F. So just like I did it previously, same thing I'm going to do here. I'm going to put down the values of y1, x1, y2, x2 into this equation. Once I put these values and solve it step by step, I'm getting this R by C into F value as 8.2, which is justified. You can see here, if 0.39 lies between 0.631 and 0.264, then obviously this 8.2 is between 5.79 and 12.8. That's correct. Now I'm going to use the equation of this R by C into F. Obviously, R is known to me since diameter is 70, R is 37.5. Radial clearance value is given to me 0.03. This will go and multiply here, or I can divide it here like this, and I can find out. This will come into the denominator. Sorry, F is 8.2 divided. This will come into the denominator. The answer is 0.006. Very easy numerical if done step by step. Let's proceed to the next thing. What have they asked to us? They are asking what is your power lost in friction, and directly after that heat loss is asked. Power lost, heat loss, it's one and the same thing. 2 pi ns FWR divided by 10 raised to 6. If I want to bring this in numerator, it will become 10 raised to minus 6. Ns is n upon 60, RPM divided by 60. F, we already found out right now, 0.006. W is given, R is 70 by 2, 37.5. I'll get the answer as 0.023 kilowatt. That is your power lost in friction. That is your heat loss. What is the next thing that is asked to us? Total flow Q and side flow QS. First, let us find out total Q flow. Same thing. For 0.39, if I want to find out, I'll have to use the interpolation equation. Y1 minus YR is X1 minus XR. Y1 minus Y2 is X1 minus X2. Putting all these values properly, I'm going to get the answer of total flow Q I'm going to get the answer of total flow Q That is in mm³ per second I want. But before that, this is not Q. This is not directly Q. This is Q upon RC NSL, as you can see here. This is Q upon RC NSL. So if Q upon RC NSL is 3.85, then the rest values I do have in the given data. I have the value of R. I have the value of clearance. I have the value of revolutions per second. I have the value of bearing length. Simply all this will go and multiply over here with 3.85. I'll get total flow as 2165.625 mm³ per second. Sometimes they tell us to find out in liters per minute. So you'll have to do the proper conversion of units. Such numericals also have solved it before. You can find out. Moving ahead, side flow. This QS is your side flow. That's what you have to find out. So same thing. For 0.39, which lies between 0.631 and 0.264, the Sommerfeld number, I'll have to find out this value somewhere, which is going to lie between 0.280 and 0.497 QS by Q. So same thing I'm going to repeat. If this is X1, this is Y1. If this is X2, this is Y2. And 0.39 is XR. Then in front of this, what is this YR, QS by Q value? That's what I want to find it out. I'll put all these values from here into this equation. Y1 minus YR upon X1 minus XR is Y1 minus Y2 upon X1 minus X2. Unknown YR you can find out by simplification properly, step by step, which I've done over here. So I found out QS by Q as 0.4225, which is justified. You can see as 0.4225, lies between 0.280 and 0.497. But this is QS by Q. Q I've already found out before in the previous step, which is 2165.625. We'll go over here and get multiplied like this. So the answer is 915 mm³ per second. Last thing they've asked is temperature rise, delta T. But they've not specified us certain values, or they've not told us how to do it. We'll neglect the effect of side leakage. And we'll proceed with this equation: 2 pi NSFWR upon rho QCP 10 raised to 3, where rho is the density. Standard value 860 kilogram per meter cube. CP standard value, specific heat 1.76 kilojoule per kilogram degree C. Everything I have it with me. I'm just going to put down into the formula and I'm going to get the value. I have 2 pi 400 by 60 ns. I found out coefficient of friction. I do have the radial load. I have radius of the journal. Don't forget this. I do have rho, which is 860. I have found out Q, which is total flow, 2165.5625. And I have CP value, which is here 1.76. Properly inserting the values in the calculator, you'll get 7.2 degrees C is your temperature rise. Thank you.